amino acid and the fact that amino acids have like part of their structure, their chemical formula is exactly the same with all 20 of the amino acids, right? So that's the part that's in like a beigey look here, that nitrogen, carbon, carbon. So you notice that every single amino acid has that beige part that's the same. Nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon. The part that differs is the part that they highlight in purple. So they call that the R group. They called it R because they said it was the residue group. So that's where R came about. So the R group is the one that can have one of three properties. It can be ionic or polar. Those are hydrophilic. Or it can be nonpolar, which is going to make it hydrophobic. This is going to come into play in affecting how a protein folds up, because you know that things that are nonpolar do not want to mix with things that are like water. So therefore, they're going to have a folding that's going to change that. So the first level of structure is, well, and then the last thing that we did talk about when we quit was really about like dietary sources of protein. Where do you get protein? What is protein for? You know, why do you need protein in your diet? You have to have protein in your diet to get the essential amino acids. Those 8 amino acids that you cannot make. If you do not ingest enough protein, you become protein deficient. And so that means you can't make the proteins that your cells need, and you're going to end up with some kind of deficiency, whether it's anemia because you don't have enough protein in your diet, or maybe you just have a weak immune system because you don't have enough protein in your diet, or maybe you don't heal as well because you can't make collagen because you don't have enough protein in your diet. So that's really why you need protein to supply the amino acids so you can build the proteins that your cell needs. So the structure of proteins, they say there's 4 levels of structure. The simplest level they call the primary sequence. The primary sequence is just the sequence of the amino acids in the protein chain. So amino acids combine in a condensation reaction. So if you remember that back from chapter 5, condensation reactions are reactions that form water. So they are going to pull 2 hydrogens and 1 oxygen off of 2 molecules, and by doing that, it's going to link them together. So you remember how carbohydrates did that with the glycosidic bond. So the glycosidic bond, you had 2 sugars, you pulled a hydrogen, you pulled an OH off, that caused them to join together, forming that glycosidic bond. Same thing here, except when we have amino acids linking, what ends up getting pulled off is you lose the oxygen from one of the amino acids, and you lose 2 hydrogens from the other. And so there your H's and your O combined, making water. So notice that water is a product. And that forms the connection between these 2 amino acids. So the carbon, the end carbon on this amino acid becomes joined to the nitrogen on the next amino acid. So can you see it here? This link right here, they call that a peptide bond. So peptide, the term peptide just refers to little protein. So peptide bonds are just the bonds in proteins. It's just the bonds that link amino acids together. Every link requires a condensation to get to, and water to be formed as a product. So let's link these. Here are 4 amino acids. So can you see that this is amino acid 1, 2, 3, and 4. So all of those, notice that NCC, 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 all across the top, that's exactly the same. The only thing that they differ by is their R. And I didn't even put in specifically what they are. We're just going to say R1, R2, R3, and R4, just to indicate that they're whatever R group for that amino acid 1, 2, 3, and 4. But now if we link these, so if we're going to link them, we are going to pull oxygen off of the carbon on the first amino acid and pull the 2 hydrogens off of the nitrogen from the second amino acid. So there is a water that will be formed. Use a darker color. So now the end nitrogen doesn't change. So the end nitrogen is still an amine and has a positive charge. The middle carbon is not affected. That middle carbon is the one that has the R group on it. But now this third carbon, so the third carbon still has its double bond oxygen, but it loses the other oxygen. The other oxygen comes off, and instead, the link is formed between this carbon and the nitrogen on the next amino acid. So now I have the link, and this is the peptide bond. So this nitrogen, so I lost 2 hydrogens, but that nitrogen still has 1. So there's still 1 hydrogen left. What's next? There's a carbon, and above would be hydrogen. Below would be the R2. Okay, that's the middle carbon of the second amino acid. The end carbon, what's attached to it? That double bond oxygen, but it's going to lose its oxygen. That single bond oxygen gets pulled off in a condensation reaction. So this carbon gets connected to what? The nitrogen of the third amino acid. So here is the next peptide bond. That nitrogen still has 1 hydrogen. This carbon has a hydrogen above, and below would be what? It's the middle carbon of the third amino acid. What's below? R3. Okay, so notice it's a pair. And then on the end, carbon, double bond oxygen, loses an oxygen, forms this peptide bond. So the next bond is 2A. Another nitrogen, the last nitrogen. The nitrogen on the fourth amino acid is this connection. It still keeps 1 of its hydrogens. Middle carbon has a hydrogen above, and R4 is connected below. So notice that doesn't change. The middle carbon is not really affected by a peptide bond. It's just the nitrogen and the carbon that had the oxygens on the end. And so this last one keeps its 2 oxygens because it hasn't been linked to anything. But here are 3 peptide bonds. The bonds between the nitrogen or the carbon of one amino acid and the nitrogen of the next amino acid. Now I have a protein chain. I just have 4 amino acids linked together. Depending on what those amino acids are, whether it's glycine or alanine or phenylalanine, remember the ones we were like mentioning, cysteine, methionine, depending on which ones those are, they call that the primary structure. So it's just the order of the amino acids. So if you saw a structure, you should be able to pick out how many amino acids in this protein, right? You just count the NCCs. So 1, 2, 3, 4. So you can see there's 4 NCCs repeating. So that tells you that there's 4 amino acids in that protein. So a connection to this is what happens in celiac disease. Celiac disease is a disease where somebody becomes allergic to gluten. So gluten in the last 5-10 years has really had a really bad rap. Everybody's like, gluten's terrible for you. Everybody's like, you shouldn't eat gluten. People are like, I don't know what gluten is, but you shouldn't eat it. We eat stuff that says gluten-free because that means it's good. Not necessarily. All that gluten is, it's a protein found in grains. That's it. It's just a protein, okay? It is a protein found in, specifically, wheat. Now think about all the stuff that's made of wheat that you eat. So any kind of bread, wheat. Crackers, wheat. Cereal, wheat. Almost everything that's any kind of carbohydrate, wheat. Anything that's got wheat or barley, buckwheat, any of those grain types, they all have gluten proteins contained within. Things that don't have gluten, rice. Okay, so rice, it grows differently. It's a different kind of grain seed, but it does not have gluten. Oatmeal doesn't have gluten, but a lot of places that process oats actually process wheat as well. So some people that have actually have celiac disease, they have to be very careful about eating oats. Potatoes do not have gluten, okay? They're starchy, but they do not have gluten as a protein. So that's pretty much it. If you have celiac disease and you eat things that are wheat products, your stomach digests the protein from that grain, the gluten protein, and it creates pieces because you have this long protein chain and the digestive enzymes in your stomach break it up. Unfortunately, when these pieces get into your small intestine have immune cells that kind of monitor what's there and what gets absorbed. And you actually have an immune response to these gluten fragments that cause inflammation of the lining of the small intestine. So when things get inflamed, they get very sore. So any food passing by rubs against this swollen lining, creating pain, cramps, gas, nausea, the whole 9 yards. Like it is like very, very painful. So I had a friend before he was diagnosed with celiac disease, he literally lost 40 pounds because he got to the point where he just stopped eating altogether. He was like, it doesn't matter what I eat. Anything I eat is just sharp pains. So he was just like drinking protein shakes and like drinking water. He was like eating very, very little. And it was because his small intestine lining was so inflamed, anything, whether it had gluten in it or not, anything coming through was creating those pain sensations. So what they had to do is they had to put him on steroids because steroids decrease inflammation. Put him on steroids to help decrease the inflammation, and then put him on medication to help block this inflammatory response that his immune system was having, which then makes him immunosuppressed, which then makes him at higher risk of developing other kinds of infections, and like respiratory infections become big, bronchitis, pneumonia, and all of that. So there's a lot of negative side effects associated with it. So that's really what true celiac disease, it actually does this. I like that picture that's over on the left. This is what your small intestine lining should look like. Your small intestine lining, it has these little microscopic projections. So the surface of the lining actually has all of these little finger-like extensions. I think of it kind of being like thick carpet, okay? And so when food moves through your small intestine, which is, it's 20 feet long, but as food moves through, it actually hits these little fingers. So it gets down into the little nooks and crannies. That increases its absorption. So that is why we can have food pass through in about 3 hours and nutrients get absorbed. All the nutrients that are in that food get absorbed. What doesn't get absorbed ends up getting excreted. But that's because you have this huge surface area. So just think about food kind of going like this and in and around, okay? With celiac disease, this inflammation causes damage to those little villi fingers. And so they begin to shrink. So they begin to get smaller and smaller, and eventually you end up with a surface of your small intestine that's like this. What's that going to do to your surface area? Decreases it. So now when food passes through, it doesn't hit the walls. Food actually can pass through and never come in contact with the surface because the surface is just like a smooth tube instead of having all of those folds to it. That decreases intestinal absorption. Low intestinal absorption can actually lead to malnutrition. So this is the reason the guy lost 40 pounds. Is one, he did decrease the amount of food he was eating, but the food he was eating, he was not absorbing because it was seriously limiting the processing that needs to go on in the small intestine. So that is really what happens with people that have true celiac disease. It is something where they have to avoid wheat and any kind of gluten-containing grain foods at all costs because they end up risking malnutrition. So the other guy I know, he was diagnosed with celiac disease when he was in his 20s, and he's like in his 50s, but he is like religious about checking everything. And if there's a question, because like gravy can have flour in it, flour comes from wheat, okay? So like you don't think about anything that's a thickener, wheat. So you worry about all of these. And so he is like rarely eats out because you don't know what sauces actually have. And he's like, I have been through enough bouts of pain in my life that I know now I would just as soon eat rice and potatoes for the rest of my life than to actually suffer from that. But he is like super skinny. So again, he struggles with that malnutrition because that kind of damage does not repair easily. Regrowing, remove, like putting those villi back, it's not an easy process. And so people that have celiac disease ending up with this flat little small intestine lining is really the big challenge. That's just because of a protein. It's because of the sequence of that protein in gluten that triggers this immune response. Other proteins don't. He can eat meat, he can eat any kind of animal product, doesn't cause a problem. It is the specific sequence of gluten when it's digested in the stomach that creates this autoimmune response. And I'll try to give you an example of how like this structure thing affects certain kinds of diseases as we go along. So that's the first example. So primary structure, it's the order of the amino acids, and celiac disease is an example where that order is a problem. Secondary structure is what happens when that nitrogen carbon chain, right? So they call that the backbone of the protein, because the nitrogen carbon of the amino acid is linked to another nitrogen carbon of the next amino acid, and so on and so on and so on. Right? So remember in this. So if we're talking about, talking about this. See how that just repeats? NCC, NCC, NCC. They call that the backbone of the protein. So those R groups just hang off of this chain. So that creates a chain. Well, the nitrogen, remember that nitrogen is electronegative and it's got a hydrogen. And then we have a double bond to oxygen there as well. So when nitrogen has a hydrogen and you have an oxygen, we can have hydrogen bonding. So along that chain, hydrogen bonding will cause this chain to twist. It'll twist and form into a helix. So in looking at this one over here, if it lets me, see if it'll let me. Yeah. So can you see where the carbon with the double bond oxygen has a ... to a nitrogen with the hydrogen? If you look at this chain, this creates what they call an alpha helix. So if you think about something that's just straight, that's like a straight thread, no twisting, no bending, no nothing, if you pull on that, there's not a lot of flexibility. But what if I pull on this coil? Think of like a slinky. What happens when you pull on the ends? They stretch out, and when you let go, they come back. So adding this alpha helix adds a lot of flexibility. So now we've got a chain that can kind of do this bending back and forth, and it can be stretched. And if it's stretched, it has the ability to stretch without breaking. So this helps to make this helix a very strong structure. I think about it as being very flexible. Because some proteins have 400 amino acids. So they're not just 4 amino acids, they're super long. So if they were just a straight chain with no ability to give flexing or bending, then if there was a force that pulled on it, it would snap. Because these are just a single covalent bond holding these atoms together. So they wouldn't be as strong, but by having this coiling, it creates this flexibility and makes it a little bit stronger. So they call this an alpha helix, which is just because of the way that it coils. If you just remember, secondary structure is when the backbone of the protein forms a coil, adding flexibility. It can also, though, the backbone can also kind of fold back and forth. I think of it looking almost like a zigzag. So it folds this way and back and this way and back, and that forms what they call a pleated sheet. So again, think if you took a piece of paper and you folded it back and forth, back and forth. Do you remember making a fan when you were a kid? Okay, so you could take that and you could fold it down, or you could pull it out. Fold it down, pull it out. So having that pleated arrangement, again, gives you this flexibility. So it's going to help keep the protein from breaking if you pull on it, and it can go kind of like snaps back into its place. So they call this arrangement a pleated sheet. It is still considered secondary structure because it's the NCC, the backbone of the protein chain, that's actually doing that. So it's not the R groups. The R groups aren't involved in this. The R groups are basically just hanging off, but it is the nitrogen and the carbon of that backbone to form these hydrogen bonds. And that creates both the pleated sheet and the helix and help to really improve the flexibility of a protein. So an example of changes with this is what happens with Alzheimer's. So Alzheimer's disease is characterized by, first, the person becomes somewhat forgetful, stops doing, like, they have, like, their short-term memory gets worse. They might remember things that happened 20 years ago, but they can't remember what they did 15 minutes ago. Okay? Over time, it can increases, and then they start to forget who you are, even though they've known you your whole life. Or they might think, like, I a friend that had a father with Alzheimer's, like, he just started mistaking his daughter for his wife because she looked like her. And so it's like that whole time issue becomes a problem. As this disease progresses, if you do brain scans of brain activity, you see loss. So there's loss of brain activity over time and scar tissue that begins to form within the brain itself. And that's why you have this loss of memory. You have this sort of loss of normal functions. They eventually begin to actually regress. So they become more childlike in their behavior. And worst case scenarios, they get to the point that they like lose control of bowels. They also they forget how to eat. Okay, so they say that they become more childlike, even going all the way back to like toddler and then even infancy. So really have to have like complete care. And it's all because of this loss of brain function. It's really based on changes that happen in the proteins of the neurons within the brain. So normal neuron connections have alpha helix. So see the red, it looks like alpha helix to me looks like curling ribbon. Right? So, like you pull curling ribbon like presents and it always does this automatic twist, okay? That's really what the alpha helix looks like. That's normally found as the connectors for brain cells, which are neurons. Somebody with Alzheimer's, though, those protein, they lose that alpha helix, and instead you find that they form these beta plaques. So these plaques are actually where the proteins, instead of having the coil, they form that pleated sheet arrangement, but then they begin to stick together. And when they stick together, they form these bundles that actually interfere with neuron function and eventually cause neurons to lose their nutrient and oxygen supply, so those neurons die. And when the neurons die, then you lose that function that the neuron had. So there is, now that they understand, it's actually changes in secondary structure of proteins found in the brain. Now, knowing that, they're doing research on, well, what triggers this change? Why does it go from being an alpha to a beta? From the alpha helix to that beta pleated sheet type? Why does it end up switching? What causes these proteins to fold up wrong that leads to the development of Alzheimer's? So there are now medications that help to suppress this change, so it helps to slow the progress of Alzheimer's, and there's a lot of research into it, but it's really like all the way down to the structure level within the brain. So there's that question, but then why is it like for some people, it's like at what age is it triggered? At what age? Why does, for some people it happens when they're in their 40s, some people they're in their 70s, like what triggers this change to start happening? So there's still a lot of research that they're doing, but they've gotten all the way down to this understanding that on a cellular level, these are the changes that are happening in the brain that are leading to this disease. So that's the example for secondary structure. So remember, like that coiling or the folding, the pleated sheet of the backbone is what really creates this sort of flexibility to the protein. Tertiary structure. Tertiary, third degree of structure. So it's the third level. This is because of the R groups. So nothing we've talked about has been because of the R groups. So remember when we looked at the amino acids, I said you got like 9 amino acids that are nonpolar. They're hydrophobic. So if you put those in water, they are not going to want to interact with water. They're going to be like oil in water. And instead, R groups that are nonpolar or hydrophobic, they're going to actually want to come together in the protein. Remember the micelle? Remember when you put soap molecules in water, how they form those soccer balls and the nonpolar tails go into the center? That's really what happens for a protein. If you have any hydrophobic, nonpolar R groups, they're going to all come together. And so you might have this helical coil, but if there's some nonpolar amino acids along that coil, they're going to change the helix. They're going to go, they're all going to want to come together. And now you're going to end up with funny little helix, but you're going to end up with those nonpolar groups, those R groups clustered. So I always think they really like to bury themselves into the inside of the protein, because if they're inside, they don't interact with water like the micelles. The other two, though, polar, remember we said there were six polar, and then we had the ionic, the ones that actually had a charge, where the nitrogens with a positive charge, oxygens with a negative charge, that were part of the R group. These are very hydrophilic. So these ones like to interact with each other, and they like to interact with water. So hydrophilic R groups are going to like to be around the outside, or they're going to cluster together because they're similar. So that's where this whole polarity thing comes into play. This gives you a lot more folding than just secondary. Secondary was just a coil or a pleated sheet. But now look, if we add the third level of structure together, now you get proteins that look like this. So this purple string, primary structure is just the order of the amino acids. Secondary structure, do you see any coiling? Yes, so that's alpha helix. So you can see kind of like areas of coiling. Do you see that one area down low here where it folds back? That's like a beta pleated sheet. So that's where the chain folds back on itself. See hydrogen bonding between those two sides? That helps to create this flexibility and stability. But that one area, like right here, so this area over here, and this, around where this salt bridge area is, so this probably was just a long coil. But I had a positively charged R group and a negatively charged R group, and they want to form a salt bridge. They want to have, because remember, that's ionic, which is like the strongest of the intermolecular forces. So they're like, oh, like magnets. So see how it looks like that helix, like bent in half to create this coil? It's all because of the R groups. So in there, you can see there's some hydrogen bonding with water by R groups. There's some hydrogen bonding between hydrophilic R groups. There is this area here. So this area, these are all hydrophobic R groups. So see how they're all clustered together? So you see like a CH3, nothing but carbon and hydrogen. An aromatic group, nothing but carbon and hydrogen. So these ones are all going to want to come close together because they're nonpolar. They're not going to want to interact with the watery environment the protein is in. They don't want to interact with any of the hydrophilic R groups. They end up clustering together. And so do you see how this makes a shape, right? So now this protein has a shape rather than just being a coil, rather than just being that pleated sheet or just being a loose thread. Now it has this shape that is stabilized because of tertiary structure. The more tertiary structure that you have, the greater the globular protein shape you have. So that when I think of globular, I just think about a glob, right? Like a big dollop of whipped cream. So a glob of it is sort of like a term we use at our house. I would like a glob. Okay, so think of that as being kind of more three-dimensional, round, spherical. The more tertiary structure, the larger, more complex the folding is, the more globular your protein tends to be. Best example of globular proteins are things like this. What did I use when I drew this? What did that represent? Do you remember that? Way back again in chapter 5. Well, those are the villi, but this is supposed to be a protein. What protein has a very folded shape? Enzymes, okay? So enzymes typically have a globular shape because their shape allows them to interact with substances and speed up chemical reactions. So we'll actually talk about enzymes at the very end of this chapter because it is one of the big functions that proteins have in the body. Examples. Here is a globular protein. So notice it's very folded shape. You can still see helixes in it, but it's folding. Instead of just being like a piece of curling ribbon, its folding is all because of the R groups, hydrophilic, hydrophobic interactions that create this folding. Globular proteins fold into a very spherical shape. Typically, things that are hydrophilic, the hydrophilic R groups are on the outside, hydrophobic R groups are on the inside. Great example, enzymes. Fibrous proteins are another kind of protein, and like this image is nowhere near as big as the other one. See if it will let me magnify. It probably won't. Okay, so here's two. So there is keratin and collagen. So does anybody know where's keratin? Hair, nails, and skin. Your entire surface of your body, minus like your eyes, okay? Entire surface is lined with cells filled with keratin. They call keratin a waterproofing protein. And if you look at keratin, do you see that it's two proteins that are twisted around each other? So it really looks like just a thread. So microscopically, it's these very flat thread-like structures that, in terms of waterproofing, they are very hydrophobic. So hydrophobic, does it want to interact with water? No. So if the inside of the cell is hydrophobic, then it's not going to let water in. So that is what the surface of the skin, the hair, the nails, that helps to make a really solid, firm, strong type of structure. So when you think of fibrous proteins, your skin, hair, nails. The other example, though, is collagen. And we'll actually talk about collagen again because it's a huge, important protein, most abundant protein in the body. Collagen is what makes up all your connective tissues. So when you think of connective tissues, we're talking about bone, cartilage, tendons, ligaments, all of the dense, regular, and irregular connective tissues that hold your surface layers on. All organs are wrapped with a cover, all connective tissue. Okay, so connective tissue is kind of like the framework of the body. It helps to anchor things. Collagen is the purple thread, and it's actually made of 3 proteins, but those proteins have really nothing but alpha helix. So it's kind of like long alpha helix chains, but when they wrap together, that makes them really strong. That helps to make it really durable. So this is why tendons anchor muscles to bones. And most people never have any problems with their tendons over the course of their lifespan. Ligaments anchor bone to bone. They're nothing but strands of collagen bundled together, thick enough to be able to withstand quite a lot of force. Those are called fibrous. So just think of fibrous as looking like thread-like. Fibrous proteins tend to be more anchoring, more framework, more structural in their arrangement, whereas enzymes and globular proteins, their shape is what helps them function. Okay, having this 3-dimensional shape is really what's important. So you tell me, here is a protein. One, how many amino acids in this protein? You tell me. More than 1. There's more than 2. 8. Did everybody see 8? Okay, so notice if you go along the part I've boxed out, you see NCC, NCC, NCC repeating. Every N would be an amino acid. Okay, so if you go along that backbone and just count the number of N's, then you'd be good. You would be able to figure out there's 8 amino acids. So which of these, and these are the R groups. So looking at the R groups, you tell me which R groups are hydrophilic. What about the first one? Yes or no? Yes, because it's got oxygen, right? Remember, you look for a nitrogen or an oxygen. That's really the big kicker. Small molecule, nitrogen or oxygen, it's hydrophilic, it's polar. What about the second one? Hydrophilic or hydrophobic? Philic, because see the 2 nitrogens at the end, or 3 nitrogens at the end. In fact, this pen's. In fact, one of them has a positive charge, so this is actually ionic. What about the next one? This one is hydrophobic. Hydrophobic because do you see that that R group is nothing but carbon and hydrogen? There's just CH, CH3, CH3, nothing but carbon and hydrogen, so it is hydrophobic. What about the next one? So there's the carbon with that aromatic ring, but on the end is a OH, so that's going to make it hydrophilic. What about the next one? Hydrophobic, because can you see that it's nothing but carbons and hydrogen? Next one, hydrophilic. See that it's got a nitrogen. If it's got a nitrogen or an oxygen, then it's going to be hydrophilic and polar. Next one. Next one's really strange. Do you see how it looks like it's like a ring attached to the chain twice? That's proline. So it's actually like a CH2, CH2, CH2. So if it's only CHs, it is. So it's going to be hydrophobic. And then the last one. Hydrophobic as well. If you don't see a nitrogen or an oxygen, hydrophobic. If it's nothing but carbon and hydrogen, those are going to be hydrophobic. So if this one folds up, the ones that are hydrophobic are all going to try to cluster to each other. So that's going to create this folding. The more hydrophobic R groups, the more folding you're going to see. Okay, because they're not going to want to be on the outside with water. Last structure, fourth level of structure. Not all proteins have this structure. In order to have this structure, you have to have more than one protein chain. So you have two or more chains. That forms quaternary structure. So we've already talked about two. Keratin. Keratin has two thread-like proteins that like wrap around. So keratin. So one of the chains is like this. The second chain wraps around it. Collagen. Collagen has three. So collagen has three thread-like proteins. If these were single strands, they would not be very strong. But the fact that they're double-stranded, triple-stranded, it's actually, if you look at thread, like thread that you sew with, if you get a magnifying glass and look at it up close, looks just like collagen. It is actually multiple strands of string that are actually wrapped together, because by wrapping them together, you increase the strength dramatically. Just one single strand and you could snap it. But if you have multiple threads wrapped, that's going to add to that stability. So collagen actually has three alpha helix structures that are all wrapped together. And that's going to give it that strong thread, durable structure. So it doesn't have a lot of tertiary structure because it's just like little alpha helixes, but it has that quaternary structure because it's more than one protein. The example that they use is looking at hemoglobin. So this molecule here, and it actually goes through all the levels of structure, okay? Primary structure, remember, this is just the sequence. It's which amino acids are linked together into the chain. Secondary is when the backbone forms a helix or pleated sheet. Tertiary is the R group. That can form globular if you have lots of tertiary structure. If you don't, then you tend to have more fibrous structured protein strands. And then quaternary is if you have more than one protein chain. So multiple proteins coming together. Hemoglobin is an example of this. So hemoglobin is another one that we're going to talk about in terms of function. So hemoglobin is found where? It's in your what? It's in red blood cells. So hemoglobin is a protein that is found. I'm so tired of my pen. I'll throw it across the room. It's in your red blood cells. And they say if you pulled all the water out of a red blood cell, pretty much all you would have left is hemoglobin. So it's like 98% of the interior of a red blood cell is hemoglobin. Hemoglobin is actually made of 4 proteins. And if you look at this image, do you see that there's kind of like 2 purple globular proteins and two gray-looking globular proteins. So the two that are purple, they're very similar in structure. The two that are gray are very similar in structure. Those proteins contain, do you see in the very center, can you see this little like red thing with the little yellow circle? Does anybody know what hemoglobin has? What is the one thing in hemoglobin that makes it kind of unique? It's the reason that red blood cells are red. What's in them? Iron. That's an iron. Okay? So there's 4 iron atoms in each hemoglobin. So each has an iron atom. It's arranged as a heme, so it's kind of like iron is like held in this pocket within each of those protein chains. All by itself, a single hemoglobin subunit, because it has iron, it can bind oxygen, but not very good. But when you put all 4 of them together, they actually complement each other, and it causes a slight change in the shape of the 4 proteins. And now, as this complex with all this quaternary structure, all 4 of those proteins, each of them binds oxygen, and they bind oxygen better than they would if they were single. So if you only had a single protein chain, it wouldn't bind oxygen very well. But when they fit together, that actually causes them to change shape slightly, and it increases their ability to carry oxygen immensely. So in one red blood cell, so first, each hemoglobin can carry 4 oxygens, 1 in each. So those iron binds 1 oxygen. Iron binds an oxygen. So 1 hemoglobin protein can carry 4 oxygens. 1 red blood cell has about 1 million hemoglobin proteins. So that means 1 red blood cell has the ability to carry 4 million oxygen atoms, which just seems crazy. It seems like an awful lot when you think about 4 million in 1 cell. And 1 drop of your blood has about 5 million red blood cells. And that's just a drop of blood. And you have about 4.5 liters of blood in your blood vessels. So that's like huge amounts of oxygen that ends up, but they're supplying oxygen to trillions of cells. Right? You are trillions of cells. So that makes sense then when you start to think about, okay, so I've got trillions of cells, and some of those cells are constantly demanding oxygen. Brain cells have to have oxygen supply. Heart cells have to have oxygen supply. Okay, so this demand, this is how you end up getting that much oxygen to all of those cells consistently 24/7. It's because of these red blood cells. If you don't have enough iron in your diet, you can't make hemoglobin. So what do you end up being? Anemic. Don't get enough protein in your diet, can't make the hemoglobin protein chains, and you can end up being anemic as well. So you've got to be able to have the iron for the hemoglobin to work, but you've also got to be able to build the protein in order for hemoglobin and red blood cells to be able to mature. Okay? Now, if you take proteins and you alter their environment, you can cause changes to their shape. This is not such a big deal for fibrous proteins. Things like collagen and keratin, they're really pretty like hardy. They're very durable, strong. They're already solids. But if you take a globular protein, like a lot of things like enzymes, if you take a globular protein and you change its environmental condition, that globular protein can lose its quaternary, tertiary, and sometimes even secondary structure. And it ends up looking, see how the denatured one just looks like a spaghetti noodle? So it just looks like it's just laid out flat. It loses that type of folding. So what kinds of things can you do? So 1, does anybody eat meringue? Does anybody like lemon meringue pie? Okay, meringue. I'm not a meringue fan. I like the lemon, but not the meringue. So meringue is egg whites that you have taken and mixed at high speed, it starts off being that off-white kind of like gooey egg white. Like when you crack the eggs, you just take the yolk out. You've only got a bowl of whites. Starts out, those are really big proteins. Egg white is almost entirely protein. If you take and beat it, it starts to get cloudy looking, then it starts to get fluffy, then it gets kind of bubbly, then it starts turning white. And if you beat it long enough, for 5 or 6 minutes, you get this big fluffy pile. That is meringue. Okay? And so then you put it on top of your pie, you cook it for a little bit, and boom, it stays solid, it gets all brown on top. I still don't like it. But that, you are denaturing those egg whites. The egg white is all protein, and they are really big globular proteins. And that is why they will become solid. Same thing if you fry an egg. Same thing happens. It still turns white. It just doesn't get big and fluffy because you haven't beat air into it. But instead, it still ends up becoming solid. Does it go back? If I take my fried egg, put it on a plate, does it go back and become gooey again? No. Once I denature, it's permanent. Okay, so notice like the arrow, one direction. If you've got this thing that's all folded up and you shake the hell out of it, or you heat it and it ends up unfolding, it rarely folds back together. So that, most denaturation is permanent. If you add acid or base, so I don't know if you've ever done this, have you ever had to sour your milk? So if you're like making biscuits or something like that, and it says to use buttermilk, they want you to use buttermilk because buttermilk has more acid in it. So it'll actually help your biscuits to rise. If you don't have buttermilk, you can take whole milk and put like a splash of vinegar in it and let it sit. Yeah, people are like, what? It works, okay? It really just converts the milk into buttermilk. It gets kind of clumpy looking. That is because milk has a lot of protein in it. And if you add acid, it changes the hydrogen ion condition. And it causes things that are charged and ionic, they're not going to interact as much. If there's lots of acid out there, they're going to want to interact with the acids in the solution. So then you're going to start to lose this folding. And so that can cause denaturation. So if you ever have a chance to try that, just take whole milk, put a splash of vinegar in. If you have to cook with milk, it's a good thing to do. It makes really good chocolate cake if you do that. Just let it sit for about 5 minutes. And if you stir it and look at it, you'll see like little chunky stuff. That's the denatured proteins, okay? But that acidity really does help baking soda rise better, so it actually is pretty good for cooking. Application for this, okay? When you have all this quaternary structure, if you denature proteins, I said they don't fold back up. So this is what happens with lead poisoning. So lead poisoning, one common place that you might come in contact with lead is if you live in a really old house. So if you live in a house that's older than about 100, 80, 90 years old, because I think they like stopped using them in the 50s is when they stopped using lead-based paint. They used lead-based paint because lead actually made the paint stick to the wall better. So it didn't peel as easily. So you could like paint your house. You wouldn't have to paint your house for another 15 years. The paint would actually stick that well. And it didn't like lose its color as quickly. Like paint now fades. Like if you have paint that's exposed to sunlight, it'll fade really quickly. Not if it's got lead in it. Okay, so that's why it was always used. Problem though is that when the lead paint does begin to peel, if it's on the interior of the house, then peeling paint, little kid playing in their room, peeling paint on the windowsill. What do little kids like to do? Pick at stuff. So they're like, look, oh, I'm just going to pick all of this off. Oh, let me put some in my mouth. And that is because that's what little kids do, right? Everything, well, let me see what it tastes like. Believe it or not, lead paint tastes a little bit sweet. The lead in the paint triggers a sweet sensation when you put it on your tongue. So if a little kid is peeling the peeling paint off the windowsill and it's sweet, what are they going to do? Keep eating it. Yeah, this is like chiclets. This is great. So that's what happened. But now you've ingested lead. So the little kids ingested lead. This is a big issue, especially for in childhood, because their brain is growing and forming connections so quickly. Lead doesn't get excreted easily. Instead, it begins to collect and it interferes with neuron connections. So this is why they found that kids that grew up in houses that had lead-based paint, that they found on average that they had lower intelligence, greater learning difficulties, problems with like making those connections, and it was all tracked back to this. Because the lead, when it's absorbed, it interferes with brain development. So it's not as big of an issue for an adult, okay? I mean, you still shouldn't go around eating lead-based paint, but if you're exposed to a little bit of lead-based paint, it's not gonna be as big of an issue. One, you're a whole lot bigger than a little kid. When you're talking about little 40, 50-pound kids, you know, that are a third the size of you, and they're ingesting lead, that's gonna be a higher concentration, and their brain development can be affected. So that is why they took lead-based paint off the market. Now, if you buy a house and it's like was built before 1950, you actually have to have it evaluated for the presence of lead-based paint if you want to get any kind of a mortgage because of this. And if it has lead-based paint, you have to either pay a company to come and like literally they tarp the whole house. They go in and they sand with respirators on. They have to clean all of the dust because you can't just go sand this and then it shoots all over everywhere. Then you're just spreading lead-based paint in the environment. So it really has to go through this whole cleanup thing. Or you can just primer over it and paint it. Just saying, like cost-wise, that might be the only option, right? Do you have $100,000 to pay somebody to come in and tarp your house and like completely scrape all the lead paint? Probably not. Okay, so you may end up having to just primer the heck out of it all and make sure you keep it covered. Okay, and watch your kids. Like, don't be eating that. Because I know that's how my kids were like, what are you doing? Why are you eating dirt? I go, well, I just wanted to see what it tastes like. Because that's what kids are. I mean, that's all part of like their learning and exploring and such. And so lead paint ended up causing these issues. So there's just other examples. I think we covered about all of them. Soap. Soap actually disrupts the hydrophobic folding that proteins have. So soap can help to break up membranes. Remember, it helps to like pull things that are hydrophobic into the center of the soap, and that helps to rinse it off. Last topic. I'm doing okay. Last topic is the 8 functions of proteins. Okay, so these are the functions. So what we're going to do is we're just going to go through each one, and I'll just give you like an explanation and an example with each one. And in fact, 7 out of the 8 we've actually talked about already. So this will be like, remember? So hopefully it's something that's not the first time. First slide, here's 3. 3 out of 8 on one slide. Hey, messengers, receptors, transporters. Okay, and you could even think of transporters as channels if that helps you in remembering it. Messengers, hormones. Hormones are messengers. They are proteins. Insulin is a protein. Insulin binds to, first start off, insulin is secreted when your blood sugar is high. Remember, we had this whole discussion about diabetes, okay? So insulin gets secreted by your pancreas when your blood sugar goes over 110. So now insulin's floating in your blood, and it can actually freely leave blood vessels and travel through your tissues, and it's gonna bind to a receptor. Second function. Receptors are proteins that can interact with other substances. So see the green thing that is embedded in the membrane? This is a protein called an insulin receptor. So do you think that that is a fibrous protein or a globular protein? Globular, because it has, see how it goes all the way through the membrane, and notice that it's kind of got like this little cup at the top. That shape is specific just for insulin. So the shape of the receptor binds insulin, doesn't bind anything else, doesn't bind growth hormone, doesn't bind thyroid hormone. It is specific to its shape, so it only binds insulin. So those two interact. So messengers or hormones can bind to receptors on cells, and that triggers the opening of a transporter or a channel. So right next to the insulin receptor is the glucose transporter. So remember the channel? So it's an integral protein, and it's sort of like this. And initially it's closed, but as soon as the insulin binds, now it binds glucose and moves it through. Binds glucose and moves it through. So it allows that glucose to be able to diffuse from high concentration to low concentration, moving through the barrier of the cell membrane so that the blood sugar goes out of the blood and goes into your cells. And then your cells can use it to make energy. So there's 3 out of our 8 examples are right here. So remember, so hormones bind receptors. Hormones are proteins, receptors are proteins. And that will open up channels, which are also proteins. Next one. We just talked about it. Hemoglobin. Hemoglobin falls into the group of being a carrier. What does hemoglobin carry? Oxygen. So hemoglobin's job is to carry oxygen. It picks oxygen up in the lungs, it transports it to tissues, drops that oxygen off, heads back and gets more. Okay? It just keeps circulating. Red blood cells stay in the blood vessel, and they do this little circuit from the heart to the lungs, back to the heart, then to your tissues, then back to the heart, then to the lungs, and back to your heart, then to the tissues. Just does that constantly until those red blood cells get old and wrinkly and they get filtered out. Okay? They last about 4 months. Another carrier we've talked about is these. What do these carry? These carry cholesterol. So remember we talked about cholesterol and we talked about LDL and HDL. So just to remind you, LDL stands for low density lipoproteins. So these are actually protein carriers that carry cholesterol and fats through the blood. HDL stands for high density lipoproteins. So they're proteins with some lipid to them, but they're a protein and they're a carrier because cholesterol cannot free float through the blood because it's hydrophobic and the blood's hydrophilic. So they wouldn't mix. So here's a carrier. So just another example of a carrier. So carrier, think hemoglobin, think HDL, LDL as an example for those. 5, protection. You have immune system cells These cells are called lymphocytes. They're white blood cells. They're one of the groups of white blood cells that make up about 30% of your white blood cells are lymphocytes. So these lymphocytes, when they find something foreign, whether it's a foreign cell or a bacteria or even a virus-infected cell, so if they find a foreign cell, they bind to it and they find a structure on the surface of that cell that is foreign. So that's how they figure it out. So they bind to it and they're like, this doesn't fit. Remember we were talking about cell identification markers? So they find proteins on the surface of the cell that don't match what you should have, the self, right? What we normally have. So they find a foreign cell. When they figure out what's foreign on that cell, they make what are called antibodies. So they make antibodies. An antibody are proteins. They're almost always drawn looking like this. They always look like a Y. Some antibodies don't look like a Y, but the most common ones do. And so the tops of the Y stick to the foreign cell. And we're not talking about just one. So if this is your little foreign cell that has made its way into your body, and the lymphocyte finds it, figures it out, and starts making antibodies. Lymphocytes can actually make millions of antibodies per minute. Okay, so it can just start dumping out all of this antibody. So antibodies, they stick to the foreign cell. And I'm not talking like they stick 1 or 2. They can stick and completely cover this foreign cell. So the little ends of the Y stick to the foreign cell all over its surface. So, if you were a foreign cell and you're trying to be sneaky and move around through the body, how hard is it going to be when you start looking like that? Because the end of the Y, so up here is the part that sticks. This part down here is literally like an alert flag that says, this thing's foreign, this thing's wrong, something's here, it shouldn't be. Like literally it calls in all other immune cells, like macrophages. And macrophages, they like to do what's called phagocytosis. They like to eat stuff. So they will literally, because of all this antibody all over the surface of the cell, that will trigger a macrophage to come and eat it. So, huh? Yeah, it eats those too, but that's fine. We can make more, okay? The goal is you want to make sure that this little foreign cell can't stay sneaky, because if it has nothing marking it, then it floats along and keeps doing its damage, but then the cells are like, oh no, that's a normal cell, it's fine. But lymphocytes are like really specific. They like check cells. They check and feel the surface of all of those cells. And if they find one that has something foreign on the surface, then that sends up this alarm. They begin making antibodies, and the antibodies really help to bring the immune system. So they're really protective. So you can just remember, like, protection, your immune system, antibodies, great example of why you need to have enough protein in your diet. Because if you're sick and you don't have enough protein in your diet, can you make the antibodies? No. Okay, you're not going to be able to make the antibodies to be able to help fight off these foreign cells, these little invaders that make their way in. 6 and 7. Then we'll mention 8 and we'll be done. All right, so 6 and 7. 6 is contraction. This is movement, okay? So things that move have proteins that are arranged inside of muscle cells. In fact, this is the job of muscle. When you talk about like muscular tissue, whether it's smooth, cardiac, or skeletal muscle, the whole function, movement. It helps to keep us, it helps to make us move from one place to another, or the heart beats to move the blood. Blood vessels have smooth muscle to control pressure. But either way, muscle contains 80% protein, which is why when you want to get some protein, what do you eat? Meat. What is meat? Skeletal muscle. Nobody likes to think about that, but that's actually the truth, okay? So meat is skeletal muscle, and that's why it's so high in protein. 80% of the cell contains this densely packed protein. These two proteins, actin and myosin, they function by overlapping. So they initially, like that left side, they kind of look like they're overlapped this way. So you have the thick proteins and the thin proteins, but they overlap. When they get stimulated by a nerve, that causes them to interact more. And when they interact more, they overlap further. And you see how that kind of pulls them in together? I don't really have all the little legs of the myosin drawn like I should. And my pen is acting like absolutely ridiculous today. I just put a battery in. I thought it would last. But these are all the little attachments. It's funny, myosin to me looks like some strange looking spider thing, but but they do have like, they're cool. Like if you ever have the chance, you can Google YouTube this, like muscle protein contraction, like the actual proteins where you can see the little myosin like pulling on the actin. It's really neat. You're like, I don't even know how the body can do this. But it's really impressive, like that it can take this muscle, and when you contract, it gets shorter. And it gets shorter because all these little microscopic overlaps shorten a little bit. But it shortens enough so that it can actually create that movement. Anchoring, we talked about this. Collagen. So I told you that collagen is the most abundant protein in the body. You need collagen to be able to maintain your connective tissues. Collagen is used to make tendons. Tendons anchor muscle to bone. Collagen is used to make ligaments. Ligaments anchor bone to bone. But collagen is also used to make bone. All you do, the only difference is that bone has calcium added. So it's just long strands of collagen arranged kind of like rings on a tree, but then calcium is added and that's what makes it hard. Collagen is used to make cartilage. Doesn't have calcium though, but it's arranged so that it actually creates this kind of spongy structure, right? Because cartilage is kind of your cushion on the ends of the bones. All examples, all of the things that help hold layers together, you need collagen. So collagen is this big anchor. Elastin, just as an offside, elastin is found in the skin, and elastin is a protein kind of like collagen, but it has more beta pleated sheets. Instead of being more alpha helix, instead of being just like the long curling ribbon, it's a little more foldy. So you can actually take elastin, pull on it, and when you let go, it snaps back. That's why babies, their skin looks like it does. They have lots of elastin, right? So you pinch their little cheeks and they're like all thick and full and chubby, okay? And then what happens as you get older? Elastin stretches and it stops bouncing back. And when it stops bouncing back, you end up with wrinkles, okay? So hydration levels, nutrition levels, getting enough protein, you make more elastin, okay? Having limited protein, also going to affect sunlight exposure, limits elastin. So that's why people get kind of leathery face if they do a whole lot of sunbathing. So all of those can come into play as well. Last one is catalysts. And those are enzymes. And we talked about in chapter 5 when we talked about things like lactose intolerant, albinism. We talked about like PKU, missing the enzyme to be able to break down that phenylalanine. So enzymes are globular proteins that bind to a reactant and speed up the reaction to produce a product. And remember, they do that by lowering the activation energy because, and this will be the last one. So remember that I drew my little E sideways laying down. That's my enzyme, right? So enzymes have a special fold, and their folded nature allows them to interact with reactants. And we can call those reactants substrates. So if I want to take A and B and I want to make C, when they talk about enzymes, they call the things that enzymes interact with substrates. So just remember, substrates is the reactants. It's just a fancy name for reactant. So don't let that throw you if you're answering your questions. You're like, I don't know what this thing is. Same thing, it's a reactant. But what the enzyme will do is the enzyme legit will change its shape so that the substrates or the reactants get pushed together. Because remember we said in order for things to react, they have to come in contact. So do you see that now they're in contact? And remember, it's also orientation. So remember we said they can't react this way or this way. They have to land this way. Like it might be very specific the way they have to interact. And so the enzyme will bring things together in the right orientation so that they will react. And once we make C, the enzyme, once it releases C, the product, it can actually go back and do this again. So it can do this reaction over and over and over and over. So it doesn't just do it once. Enzymes don't get used up in a reaction. That's why they're really true catalysts, because catalysts just help to speed the reaction up over and over. Okay, so I will quit there. This is as far as the questions for chapter 10 will go. On Thursday, we're going to talk about chapter 11. Chapter 11 is nucleic acids. We're going to talk about DNA and RNA, some about their structure. Okay, so if you haven't done the pre-lecture for 11, you have until Thursday to